a side channel cryptanalysis. If you are the any yes, madam. I am from the any student for PhD. CRO, I am working here. Working research scholar actually. It is yeah. No, madam. Student from research scholar from the ANU. Working in the CRO. It's collaboration with MOU based PhD we are going. Yeah. What is one? What is side channel cryptanalysis? Side channel cryptanalysis in the sense everyone thinking about security. They are thinking about this software security. This is like hardware security. If you are the hardware devices leakage, side channel cryptanalysis. If you are the attacker can leak. If you have any external leakages is there, based on attack leakages, we are finding the secret information of the protocol as in the device. That is actually side channel cryptanalysis. We have already some of the cryptanalysis tool cryptanalysis attacks performed different ways. Like this is a like passive and active attacks. Two type of attacks. If you are the hardware devices, if you are not touching the hardware device, we are capturing the from the external source. That is actually passive attacks. If you are the disturbing the FPGA board or any device, hardware device, embedded device, that is comes on the passive attack. This is the some of the listed of attacks: power attack, EM attack, timing attack, memory attack, and optical attacks. This is from the passive attack. Then active attack. Most of the active attacks we can inject the fault injection. This is the active attacks in the perform the hardware devices. This is overview. Then we are giving the power attack best model. This is the one of some of the general side channel attacks like cross subkey side channel attack and side channel reverse engineering and power based side channel attack. Next. Differential power analysis and algebraic attack and deep learning side channel attack and correlation magnetic analysis. This is the survey we did in this paper. We are given like justification of the best to capturing method as well as noise free and recover easily noise recover method. Next. This is my proposed method flow. Implementation of the crypto algorithm, hardware languages and software languages. Hardware language, if you are using FPGA, I am using FPGA, I am implemented in the code of Verilog code, HDL languages. The software code for this testing purpose. If you are the model, we are going to the golden model, you have to verify the software and hardware. For that, we are taking the same crypto algorithm in the software and hardware. Test bed verification for that, then simulation with the hardware, then synthesis, bit file generation. After bit file generation, we have to go the verification of the we are configuring the FPGA, we are testing the output the configure the FPGA. Then we have to communication between PC and FPGA. Next I will explain that. Verification of the algorithm on FPGA, capturing power traces, implementation of hypothetical model and the cryptanalysis, correlation between capture traces and hypothetical model, extract the. This is combination of electronic communication as well as VLSI and crypto statistic analysis. This paper belongs to four departments actually. This is side channel provinces. We are targeting. This is the targeting board. How we are performing the side channel attack. This is the targeting board. We are taking FPGA board. Here we are generating the random numbers, plain text and key. We are transmitting the FPGA. FPGA have the encryption algorithm. We are already configure the algorithm, any algorithm, crypto algorithm. It's back to the ciphertext. At the same time, we are capturing the power trace. What is the variations of the every function, internal functions? If you are the non-linear, linear functions is there in the crypto algorithm. What is the non-linear functions have the leakages. If you are the taggle the bits, at the time the variations comes in the power variations. Based on the variations, we are capturing the power traces. Then we are doing the analysis, retrieving the power analysis. For that, we don't know where it's a long signal coming. So where is our algorithm start? Where is our algorithm end? For that, we are giving the triggering from the internally. I'm implemented in the FPGA. It will give the after completion of the algorithm. It gives the trigger to the oscilloscope. Oscilloscope we are using for the capturing power traces samples. We are taking the total samples in the oscilloscope. Based on the oscilloscope, we are capturing the power traces. Next. This is my lab setup. This here we are implemented like communication protocol. This is FPGA communication with the JTAG and USB port also. JTAG for the programming. Trigger point here we are this is the FPGA. We are giving the one nice point is in output. Peripherals taken the trigger point connected to the trigger point to the then oscilloscope one channel. Then our power traces also one channel. So look like this is the this is the setup, total setup. Here our PC generate the plain text to the gives to the FPGA through your communication, serial communication. Then it is encrypted, then written back to the PC. At the same time, what is the internal variations of the power we are capturing based on the oscilloscope triggering point also. Then after capturing the power traces, we are doing the analysis, backend analysis. Next, this is the design flow we are proposing. Start and the plain text we are giving two algorithms, Verilog, the algorithm V, algorithm C, Verilog and C language, test bed verification, then going to the synthesis. This is the top module of FPGA. What is the internally functions required for the this purpose? We are implemented in hardware language and configuring the FPGA. This is the clock generator and algorithm V and UART controller. UART controller is the main key role of the communication between the PC and FPGA. Why? Because we cannot transfer at a time 128 64 bits. It's only 8 bit only. 8 bit for that we are generated the UART controller. Communication. UART is a communication between the PC and that. Then serial communication between serial communication through MATLAB. We are implemented in the communication tool in the MATLAB language. It's generated the random number, plain text, to random number generated, it gives subbank. Then trigger point, this is a Sakura board. The Sakura have the two FPGAs actually, controller and main FPGA. Controller FPGA we are using for the communication, main FPGA we are using for the algorithm only targeting point. Capturing power traces on MSO. We are taking the help of MSO, we are capturing the power variations of the every internal power variations through MSO. Then verification of Sakura ciphertext, if it is correct or wrong. We have to verify the physical verification of the FPGA. Then after capturing traces, real traces, we are taking the real traces. We are generating software simulation code also. C language, we are generating the simulation hypothetical model for the same algorithm. We are taking the correlation. Here we are using Pearson correlation. Finally we are getting the secret information of the algorithm. That is we are proposing the method. Next. We are taking like right now AES standard one. So in that we have the 4 internal states and the plain text, that is the master key. Every internal in this substitution byte actually nonlinear function. We are targeting the nonlinear function. AES has the 10 rounds. Plain text is the 128 bit. E is the 128 bit, and ciphertext is the 128 bit. It's the 10 rounds. So every round have the 4 internal states. So for internal state, one of the nonlinear function, we are targeting the nonlinear function. What is the power variations of the nonlinear function? Every time we are taking sample by sample. That is our agenda. This is the simulation. We are taking like GTK wave simulator. We are verifying the Verilog code pre-synthesis. This is the simulation model. This is we are using one of the software GTK waveform. Next, this is the AES synthesis. We are top module. We have the all functions. What is the requirement? AES algorithm as well as communication ports and signal and clock devices also. Next, this is the FPGA. We have Sakura board. This is the evaluation board. So we have Spartan boards actually, Xilinx sponsor, but this is Japan developed for the only side channel cryptanalysis. Because of in this we have the amplifier. It gives a noise free. We don't have, if after evaluation we have the resistance capacitance, we will get some noises. So for that reducing the noise, there inbuilt have one amplifier. It will give the exactly traces. Next, this is the FPGA debugging. If you have the clock signal is a my FPGA have the 48 megahertz frequency. 48 megahertz frequency. It won't work on the. We are testing the 48 megahertz frequency. For the debugging, we are taking like XCUT is the debugging for software. Next, this is the serial communication. This is the power trace of AES. This is the like this is the 10 rounds of the AES clearly visible. We are taking like this slot only. We are taking one, every slot have the 4 intermediate stages. We are taking the only this sample, then analysis the secret difference. We analyze the total algorithm, then we retrieve the secret information of the AES algorithm. 128-bit we can retrieve. Next step. This is the Hamming for that simulation model. We are using a Hamming distance model for toggle 0 to 1, 1 to 0. This is the method. Next, this is the hypothetical model. How we are performing the how many samples required. What is the plain text? What is cipher text? Next. Thank you. So finally, we are retrieving the power traces. We are giving like this methodology. We are already exist some methods, but that is nice. We are taking some time more time than even if we required more samples also. So we are giving like 3,500 samples we can retrieve from AES algorithm. If you are going to the lightweight cipher, it's difficulty, but this method will work for the lightweight ciphers also. Lightweight means power consumption is very less, madam. So it's like AES have the 8 by 8. So polynomial equation is 8. If you are lightweight ciphers, degree is 4 only. Yes, ma'am. Actually, algorithm, madam. Actually, 10 round power traces means total AES algorithm. 10 rounds is there. So every round have the intermediate stages, 4 intermediate stages. 4 intermediate stages while working on the FPGA side, the toggling, transistor togglings is there. So power consumption is there. So power consumption we are capturing that. What is the every function? How much power consumption is taking? It's madam. It's an actual nano actual based on the parameters, madam. We are taking like minute values like 0.075. Yes, madam. Yes, madam. Yeah, similar synthesis results is the paper we are mentioned the point. This is for the presentation mode only. This is big work, so we won't mention the point at the points only. Sir. Sir. Yes, sir. Compared already compared many people. Yes, sir. Comparison we are given the conclusion. Actually, we are taking like sampling values. Yes, sir. Actually, for the comparison is difficult. Why? Because we have the many different. Can use anyone use different FPGAs? Can you use the or targeting only sample values? For that, we mentioned the conclusion. We are taking the less sample values and nice free. We are giving nice free. This is my original one. Yes. Thank you.